Okay, should be recording. I will try to keep an eye on the waiting room and make sure I admit people as they enter. And let me start with announcements. So here we are. This is the last week of classes for what has been a pretty crazy fall semester, but actually all in all, I think everyone in this class has done a pretty good job keeping up with all of the demands of the semester and all of the unusual situations we've had to deal with. So what do we need to kind of keep ourselves aware of for this last week of classes and then upcoming final exams next week? Well, the first thing coming up is the next Wiley Plus set, which is due this evening, usual time. More practice on chapter 16. Just so you know, there'll be one more Wiley Plus assignment. I'm going to make it due Friday evening of this week, 11:59 p.m., usual time. It's going to be practice on chapter 17, which is the topic of this week's classes. And I do this every semester, the last Wiley Plus set, the one I just mentioned that'll be due this Friday, will be purely for extra credit. Okay, not the one due tonight, but the last one, which will be due this coming Friday evening and will be involving practice on chapter 17. All those points that you earn on that problem set will be bonus and just added on to your Wiley Plus total as extra points. Okay, so that way you get to get a little bit of a help to your Wiley Plus total, and you get to practice with chapter 17 ideas. There will be no quiz this week. We've got enough to concern ourselves with. Okay, what else? I mentioned briefly the final exam. Final exams are next week. I'm going to say more about the final exam in detail in Wednesday's class, but I'll give you a little bit of information about it now. In normal times, the final exam is scheduled in a 3-hour block of time in the classroom that you meet, and its time and date is set by the registrar's office based on the class time. For our class time, Monday, Wednesday, Friday at 8:20 in the morning, the registrar has scheduled the final exam for next Tuesday, December 8, 8:30 to 11:30 in the morning, Eastern Standard Time. That would be in normal situations, how we would do it. We would have the final exam during that 3-hour interval. This is not a normal semester, as we know. So what I'm going to do is more along the lines of how I did the lab exam in terms of timing. I'm going to give a multiple day window, Tuesday through Friday of next week, for you to sit down and take it. Once you decide when you're going to take it, you will access it. I will explain how you will do it, how you will access the final, and you will have, once you have it in your hands, the exam, a total of 24 hours to turn it in back to me. Okay, I'll say a lot more about it on Wednesday's class. Okay, but I'm just giving you a little bit of a heads up. So you'll have a window of time, Tuesday through Friday of next week. You will pick a time that works for you based on your schedule. Once you access the exam from me, you will have 24 hours to turn it in. More details to come on Wednesday. As with regard to 110 lab, don't forget you have one more lab report for experiment 8. I have uploaded the data and the instructions on Blackboard 110L. You work with your partner, you take the data I've given you, you do the analysis for experiment 8, as is written in the lab manual, you turn in your lab report this Friday evening. That will be the end of your work on 110L. with that final lab report. I will be posting the graded lab reports for experiment 7 today and tomorrow. So you can be looking for that on Blackboard as well. And one more thing. I believe if the system is working properly, you should have received, and you will continue to receive throughout the course of this week, email reminders about course evaluations, which are done online. And you should have received one for this class. Let me ask you, please, if you would be so kind as to fill out that course evaluation online. It's very helpful information for both me and the institution. Okay? You'll get multiple reminders throughout the week, and you've got, I think, also until Friday to do it, but let me please encourage you to fill out the course evaluation for all the courses that are listed, that have been listed for you. Okay, so those are my announcements. Does anybody want to ask me a question before I get started on chapter 17? You can either type in the chat box or you can unmute. Okay. All right then. Let me talk about the first section in chapter 17. So chapter 17 is our continuation of the study of waves. I sent out the video lecture over the weekend where I introduced some of the key ideas about the kinds of waves we're studying in chapter 17. They are called longitudinal waves. And we are generically basically going to call any longitudinal wave a sound wave. The most important application of sound waves for us in our daily lives, of course, are the sound waves that travel through air, which is the mechanism by which we can hear each other. So in chapter 17, section 1, I introduced some of the key ideas about longitudinal waves. There'll be more to come in section 2 of chapter 17. And then we focused in section 1 on figuring out how to calculate how fast a sound wave travels through a medium. A longitudinal wave travels through a medium, and the medium could really be in any phase of matter, gaseous, liquid, or solid. Although we tend to focus on the gaseous phase of matter, i.e. air. Okay, so I've listed here on the slide that you should be able to see that I'm sharing, the learning objectives for section 1. And the first one is just basically you should be able to say in your own words the difference between, right, distinguish a longitudinal wave and a transverse wave. And as I mentioned in the video lecture, transverse waves were the topic of chapter 16. And the kind of toy system we studied there, just to have something specific to think about, was a taut string that would just be held horizontally, that then someone takes one end and disturbs it up and down. So the disturbance of the medium, the string, is up and down, but the disturbance itself travels horizontally along the string. That's a transverse wave, where the disturbance of the medium is perpendicular to the direction in which that disturbance travels. That's a transverse wave on a string. Or a wire, which is the topic of experiment 8 in lab. Chapter 17 is where we focus on longitudinal waves, as I have been talking about now. And in a longitudinal wave, remember, the difference between longitudinal and transverse is that in a longitudinal wave, you still have a medium, like a column of air, for example, but the disturbance of that medium, the air molecules, is horizontal in the same way that the disturbance is traveling. The disturbance of the medium is in the same direction as the wave is traveling. That's called a longitudinal wave. And that's the focus of chapter 17. Okay. Objective 2, explain wavefronts and rays. Well, I'm not going to spend a lot of time on that. I'll just say very briefly, because it's a little bit useful for picturing, visualizing, traveling of sound waves. You've got a source of sound, like a speaker of some kind, that's disturbing the air molecules and creating sound waves that are traveling or propagating outward from the source, often in multiple directions at once. And we try to visualize that propagation of the sound wave as wave fronts, where successive wave fronts represent places where the pressure in the wave, I talked briefly about that in the video lecture, has a maximum. And the distance between neighboring wave fronts is called the wavelength. We'll be drawing pictures of that kind of picture with wave fronts when we study what's called interference of sound waves in Wednesday's class, or actually Thursday's class. I'll take that back. Rays, on the other hand, just point in the direction in which the wave fronts are traveling. And the rays are straight lines that are perpendicular to the wave fronts. That's all I'm going to say about those two things. We won't do that much in this chapter with them. Objective 3, that is an important one for us in section 1. Apply the relationship between the speed of sound through a material. And that relationship depends on a property of that material called its bulk modulus, and another property which we're very familiar with, its volume mass density. Let me write down that formula right here on the screen. For the speed v of a longitudinal wave in a medium, i.e. a sound wave in a medium, square root of that property called the bulk modulus, symbol B, divided by the volume mass density, with our old friend, the symbol, the Greek letter rho. And as I mentioned in the video lecture, you can think of the volume mass density B, the bulk modulus B, as a measure of kind of how stiff the material is. How hard is it to compress? The larger the bulk modulus, the harder it is to compress the material. And vice versa. The smaller the bulk modulus, the easier it is to compress the material. That's what goes in the numerator in the formula that determines the speed of the sound wave. So the larger the bulk modulus of the material, the harder it is to squeeze, to compress, the faster a sound wave is going to travel through it. In the denominator of the speed formula is the volume mass density rho, volume mass density in kilograms per meter cubed, the standard mass density we've used most of the semester. Notice that's downstairs. That's a measure of kind of how sluggish the medium is. The larger its volume mass density, the more sluggish it is. And the more sluggish the material is, the slower sound waves travel through it. So it's that ratio of bulk modulus to volume mass density that really determines how fast a sound wave travels in the medium. Notice it's properties of the medium that determine how fast the sound wave travels. And we're going to be practicing pretty much with that formula for the rest of this class. Lastly, I'll mention objective 4, which is refreshingly simple. It says, apply the relationship between the speed of sound, the distance traveled by a sound wave, and the time required to travel that distance. Well, here, all we got to know is, assuming that the medium is uniform, we're not changing the medium as the sound wave travels along, then the speed of the sound wave is constant. So the distance traveled, if I'll call that d, is merely how fast the wave is going. Distance traveled by the wave is equal to how fast the wave is going, v, times the amount of time it's been going. I'll call that delta t. That's an oldie. That's an old kinematic relationship relating distance, speed, and time when the speed is constant. Because the sound wave travels at constant speed, assuming the medium is uniform, which we will do. So those are all the objectives. So none of the math is that hard. And there's a lot of good physics. So before we start practicing, I have included here a little table out of your book on Wiley Plus of some of the common materials through which we will be looking at sound waves and the speed of sound waves in those materials in meters per second. Now, it turns out bulk modulus and volume mass density in general depend on the temperature of the medium. So the speed of sound in a medium depends on its temperature. And the table tells us that all of these are for 0 degrees Celsius and 1 atmosphere of pressure, except where noted. And let's just look at a couple of them. Probably the most important number in this table for us in terms of doing Wiley Plus homework is the second entry. The speed of sound in gaseous air at what we would call room temperature, 20 degrees Celsius. We'll call that room temperature. Note what that speed is, 343 meters per second. That gives you a little bit of a feeling, something to wrap your head around about how fast sound waves travel basically around you in your daily life. Roughly 343 of these distances per second. Colder air at 0 degrees Celsius, you can see the speed is a little bit less, 331 meters per second. Helium and hydrogen, because they're actually less dense than air, can have sound waves traveling quite a bit faster. Then when you get into liquids and solids, you'll notice you get a huge jump in the speed of sound, much higher. Sound travels much faster in fresh water, salt water, and solids than it does in gases, because the ratio of B over rho, bulk modulus to volume mass density, is much larger for liquids and solids, mainly because the bulk modulus is so big for liquids and solids. They're very hard to compress. You can do it, but you've got to squeeze very hard. Okay. So that table is somewhat useful, and we will be referring to it from time to time, and most commonly to the speed of sound in air at what we call room temperature. Okay, so with that in mind, and you're welcome to type questions in chat at any time if you have any, I'm then going to proceed on to practicing, looking at applying situations where we have to think about how fast a sound wave is traveling in a medium. And we'll go ahead and use air as the medium. So we'll do a practice and then we'll do a Wiley Plus problem. First practice. We've got some drawings below, and in this figure, we are presented with 3 long tubes labeled A, B, and C. And they're filled with different gases under different pressures. Okay? We are told the ratio of the bulk modulus to the density for each gas in terms of a basic value, B0 over rho 0. Each tube has a piston at its left end that can send a pulse, sound pulse, through the tube. Just push the piston back and forth, disturbing the air molecules, or whatever the molecules are of the gas in the tube, and you have created a sound wave pulse that will then travel through the gas from one end of the tube to the other. The 3 pulses are sent at the same time from the left end. We are to rank the tubes according to the time of arrival of the pulses at the open right end of the tubes, earliest first. We basically want to know how much time is it going to take, right? For the sound wave pulse to travel from the left end of the tube to the right end of the tube. So you might want to think about that a little bit, how you would approach it. But if we want to find the time for the sound wave pulse to travel through each particular tube, why don't we just take the distance, speed, and time relationship and rearrange it for time. The time it's going to take a sound wave to travel from one end of a tube to the other, delta t, is going to be the total distance traveled, d, divided by how fast the wave is traveling, v. And what I propose to do is to make a table here in which we're going to have several columns. The first column will be just a labeling of the 3, which particular tube we're looking at, A, B, and C. The second column will be the total distance that the sound wave pulse has to travel in that tube. Let's do that next. Now you got to look carefully at the picture because you can see that tube C is just a straight length. Tube B and tube A are twisty, windy, but we still just want the total distance traveled of the sound pulse. We also can see that each kind of particular segment of the tube has a length L. So I'm just going to count how many L segments there are in each tube, and that will be the total distance. So for example, in tube A, we start here at the left end and we go down a distance L. Then we go to the right a distance L, then up a distance 2L, then to the right a distance L, and then down a distance L before the sound wave comes out right there at the other end. So what's the total distance big D? 1, 2, 3, 4, 5, 6L. So that's the distance, 6L. What's the total distance in pipe or tube B? Total distance traveled from left end to right end. There's a segment of length L, there's a segment of length L, and there's a segment of length L. So 3L. And the total distance traveled in tube C looks to me to be 2L. So that's the distance traveled. Now, how fast do the sound waves travel? Because the tubes are filled with different gases at different pressures. So you can't assume the V is the same. The way you tell what the V's are is it gives me over here for each tube a very important ratio. A number times B0 over rho 0. It's the square root of that ratio, that's V. So for tube A, the number I'm given is 16 B0 over rho 0. So I take the square root of that to get the V, and that would be 4 times the square root of B0 over rho 0. See what I did? I just took the square root of that because that ratio they're giving me is what goes inside the square root to give V. For tube B, the ratio is 4 B0 over rho 0. Take the square root of that, and you get 2 times the square root of B0 over rho 0. And then for tube C, it's 1 times B0 over rho 0. So square root of that, square root of B0 over rho 0. So there's the speed of the sound wave in each tube. And now I can calculate how much time it takes the sound wave to emerge from the other end of each tube. I just take D divided by V. So for tube A, that will be 6L over 4 root B0 over rho 0. I'm going to write that 6 over 4 times L over root B0 over rho 0, just to try to gather things together. But of course, 6 over 4 is 3 over 2. So let's simplify that. So 3/2 times that ratio of things that I don't know numbers for, L over root B0 over rho 0. That's as far as I can go for that. And that's how much time it takes the sound wave to travel through tube A. Now let's do the same thing for tube B. The delta T is D over V. That's going to be 3L over 2 root B0 over rho 0. So again, that's 3/2 times L over root B0 over rho 0. Same amount of time. So even though tube A is longer than B, because the sound travels faster in tube A, the sound waves emerge from tubes A and B at the same moment. Remember, they were started at the same moment. And lastly, let's do tube C. The time for travel, delta T, is D over V. So that's 2L over square root of B0 over rho 0. So that's 2 times L over square root of B0 over rho 0. And that's how much time it takes the wave in tube C. Now let's just compare these three factors out front, because the quantities in the parentheses there for delta T are the same for all three tubes. And I want to know which one's going to arrive first. Well, the one that takes the least amount of time. Well, I think A and B tie. We said that, didn't we? So A and B are first, and then the sound comes out of tube C last. Even though that's the shortest tube, it has sound waves traveling the slowest. So that's just practice with that formula that for the speed of a sound wave in a gas. Okay? Not hard, just a little bit of geometry in that one formula. Okay. So if there aren't any questions about that practice, then I'm going to do a more standard Wiley Plus example problem where we apply a real world situation, a real world application of a sound wave traveling in a medium. In this case, it's going to be in a solid. And it's taken right out of your book. Problem number 5 in chapter 17, sound wave speeds in solids. And we're going to look at earthquakes. We can think of earthquakes as sound waves that travel through the medium of Earth's crust, which of course is a pretty complicated medium. And obviously it's not really uniform throughout the globe, but we're not going to worry about that kind of detail right here. But we are going to learn a little bit about earthquakes, which generate sound waves inside the Earth. Now, because Earth, the crust, is solid, it turns out, unlike a gas, Earth can experience both transverse and longitudinal sound waves. Solids can have both transverse and longitudinal sound waves. Gases and liquids can only have longitudinal sound waves. In geology, these two types of earthquake sound waves are called, historically, S and P waves. We don't really need to know why. That's just some human beings making up names. But what we do need to know is that the S waves are transverse sound waves and the P waves are longitudinal. And here's the other key thing. Typically, the speed of the S wave, the transverse waves, is about 4.50 kilometers per second. Pretty good clip, right? 4,500 meters per second. It's a solid. And that of the longitudinal P waves is 8 kilometers per second. So quite a difference in the speed of sound between the two types of waves. Now, the way we record the presence of earthquakes, i.e. these sound waves in Earth's crust, is probably, as you know, with a device called a seismograph. So they're going to use a seismograph to record these waves at a certain location. Here's the important information. The first P wave, the first longitudinal wave, arrives 3 minutes before the first S wave. Let's assume the waves travel in a straight line from the source. How far away did the earthquake occur from our detector? Okay, all right, so how are we going to approach that? Hopefully the first thing that comes to your mind is let's draw a sketch. Let's help ourselves visualize what's going on. Let me draw a side view. You don't have to be too fancy here. That represents the ground. Below that line is Earth's crust, above that line, air. Somewhere down here, the earthquake begins. Just think of that as the source of sound waves that, technically speaking, propagate outward, away in all directions from the source. Those little arcs I've drawn are parts of wave fronts traveling outward. We've got longitudinal and transverse sound waves traveling outward from that source. Somewhere straight down, let's go in a straight line over to the right here, is our detector, our seismograph. but I'm just going to call it a detector, in a straight line from the source. And I'm going to denote the distance in a straight line between the source of the earthquake, the sound wave, and the detector, big D. And that's the thing I want. Okay? All right, now let's draw an arc here representing a wave front. Let's say it's the first wave front that has just reached the detector. Okay? That's got to be for the faster of the two types of sound waves, which is the P wave, the longitudinal sound wave, traveling straight outward at a speed VP of 8 kilometers per second. And so that's the kind of wave front there. That's the first arriving wave front at the detector. And let's say it arrives in a time interval delta t after leaving the source. I don't know how long that is, that delta t, but it took some amount of time to travel from the source to our detector. That's what that delta t is. Now, at that same moment that the first wave front is arriving with the P wave, the faster of the two types of waves, somewhat behind will be a second wave front representing the S wave, because it's slower, remember, but it's still traveling outward, but not as fast. V sub S is 4.5 kilometers per second, okay? All right, so there's a picture showing the first wave front from the P wave arriving at the detector with the wave front for the S wave delayed behind it. But it will get to the detector too, and it will get there 3 minutes after this picture, right? Because there's a 3-minute delay between the arrival of the first P wave and the first S wave. All right, now let's write down a relationship for each wave. Let's start with the P wave. We're going to use the distance, speed, and time relationship. Remember, the waves, the two types, the P and the S wave, were created at the same moment from the source. But there's a delay at them at the detector because they travel at different speeds. So for the P wave, the distance traveled is d, and the speed of travel is Vp, and the time of travel is delta t. I don't know what the delta t is, but that equation has to be a correct relationship. So I'm just going to number that, equation 1. All right, now, what about for the S wave? Well, it's also going to travel a distance d, and it's going to travel at a speed vs, but how much time is it going to take? Well, it's going to take the delta t that we saw here in the picture, but more. Because in this picture I've drawn, the S wave hasn't reached the detector yet, right? This picture is time delta t, but the S wave hasn't made it yet. The S wave needs this time delta t plus 3 minutes more. So the total time for the S wave is delta t plus what I'm going to call delta t d. D stands for delay. And I know what that delta t d is. 3 minutes is 180 seconds. And that is a second mathematical relationship. This one happens to be for the S wave. So I'm going to number that equation 2. Now, we do our math. Because we have 2 equations and 2 unknowns. What are the unknowns? D, I don't know the distance from the source to the detector. And of course, that's the thing I want. And delta t, the time for the P wave to travel the distance, d. But 2 equations and 2 unknowns, we just do algebra to solve for the unknown we want. The unknown we want is d. So we have to get rid of the other unknown, delta t. And you have a couple of ways you can do it. The way I'm going to do it is solve equation 1 for delta t, and then substitute that into equation 2. So when we solve equation 1 for delta t, of course, we get delta t equals d over vp. And then we'll substitute this into equation 2. All right, let's see what we get when we do that algebra carefully. So now working with equation 2. D equals V sub s times delta t d over vp plus delta t delay. We have to solve this for d, so let's just do the algebra carefully. Let me distribute the vs through the parentheses and write it like this. Do a little grouping. Vs over vp times d plus Vs times delta t delay. I got a d term on each side, so I got to get the d's on the same side, and then factor d minus Vs over Vp times d equals Vs times delta t delay. Now factor a d on the left-hand side, d times 1 minus Vs over Vp equals Vs times delta t delay. And now divide both sides by the stuff in the brackets. And I get a nice symbolic expression for the distance d. So I have in the numerator the speed of the s wave times the time delay over 1 minus the speed of the s wave divided by the speed of the p wave. Notice you have to do the algebra carefully. That denominator has a minus sign, not a plus. And then this is what the physicist would call a symbolic answer, because everything on the right-hand side was given to me. So now it's a matter of plugging in numbers. So let's do that. Putting in our units with each number so that we can be careful that we know what units we're going to get out and that everything is working correctly. So for the speed of the S wave, that's 4.50. I'm going to leave it in kilometer per second. As long as I list the units and keep track of it, let's see if that's going to be okay. What it means is I'm going to get the distance d in kilometers. Okay, the delta t delay was 3 minutes. We had to convert that. Well, we converted that to seconds, so 180 seconds. There's the numerator. Then 1 minus, okay, the speed of the S wave, 4.50 kilometers per second, divided the speed of the P wave, 8 kilometers per second. Notice that ratio of the V's, the two numbers have the same units, so you do not have to convert them to meters per second. The kilometers per second cancel. And then up here, the seconds cancel. And sure enough, I'm going to have a quantity, D. The answer for D is going to have units of kilometers. And when you do that in your calculator, you get 1.85 times 10 to the 3 kilometers. 1,850 kilometers. And look at that. You've got a way with a seismograph to figure out how far away the source of an earthquake was. Okay, so that's an application. That's something, say, geologists might be interested in using physics for. Okay? But it's really just using the formula for the speed of a sound wave in a medium and the simple distance equals speed times time relationship. Okay, does anybody have any questions on that example problem? Okay, so let me tell you what we're going to be doing next. in the next class, Wednesday's class. Wednesday's class is going to be about chapter 17, section 2. And we're going to get down into a little more detail about describing mathematically a longitudinal traveling wave in a medium. And we're going to focus on a sinusoidal longitudinal traveling wave in a medium. Remember, the most important wave we studied in chapter 16 was a sinusoidal transverse traveling wave on a medium, a string. So the only difference here is that it's going to be a longitudinal sinusoidal traveling wave. And we're going to write down a wave equation. It's going to involve a sine and or a cosine function. And that's what we're going to focus on in Wednesday's class. Thursday's online class will be about interference of sound waves, a very common phenomenon, and something that acoustical engineers are very concerned about. And then Friday's class is going to be about one of the most important applications of wave travel, the Doppler effect, which is used in many, many, many different situations to study on the medium of a sound wave. So that's the plan for the week. I will say more, as I said at the beginning of this class, I will say more at the beginning of Wednesday's class about the structure of the final exam next week. This is, other than the fact that we're all at home, presumably, or someplace like that, this is a normal week. So I have my normal office hours. I can be contacted through email. We can set up different times to meet based upon, your schedule. And you have homework tonight, and then bonus homework due Friday night. No quiz this week. Okay. All right, that's all I've got. So if there aren't any questions for me, that will be where we will stop for today. Thank you. You too.